going to start recording there. Okay, so I've got two different ways it's recording, and so one of them's bound to work. All right, so first off, I'm glad everybody's here. So today is liable to take around 2 hours. Okay, there's a lot of material to cover. We will take a break. I promise you that. We will take a break, but please don't go away. Please don't go away. All right, when we take our break, because important stuff, important instruction will follow. Okay, and so we'll do that. Now we left off. Where did we leave off last time? We did units. You know, what's the different kinds of units, and it's really important to have units and that sort of thing. And and that's about as far as we got, I believe. Okay, so first off, whenever we have measurements, we have a unit, we have a number, right? Well, let me show you how to do a measurement, and this is particularly relevant for today's lab, okay, for lab that's due Saturday. By the way, lab's due Saturday. Don't wait to the last minute to do it, okay? So let me go ahead and start sharing, and if at any point I'm sharing or I'm talking about something and I say, you know, this and that and it ain't there, please stop me because it means I forgot to hit share. So everyone should see a ruler. Does everyone see a ruler? Thumbs up? Yes? No?
Yes.
Maybe? Everybody see a ruler? Can you see a ruler?
Hmm.
Did I just lose everyone?
Now we see it.
Oh, you
I
do
can
see
see
it.
it.
You do see it? Thumbs
Yes.
Yeah.
up? Thumbs up?
Yes.
Okay. All right. So here's a ruler. And in the lab number 1, we have to be able to use a ruler. Now, this ruler has a centimeter side and it has an inch side. Now, as far as the inches go, you just estimate in between for whatever it is that you have. So let me go ahead and let's see, slideshow, review. We're going to start inking because this one's actually a PowerPoint slide. So let's say that you're trying to measure something with this ruler. Okay, and let's say that it is right there. Okay, can everybody see the arrow on my ruler? Okay, well, apparently I lost the other piece, but there it is. Okay, now the way you read any sort of measurement is you have what are called certain or known digits, and we have estimated digits. Now look, the certain digit means everybody in this room agrees. In other words, there's no question that it's a known number, that we know what it is. And estimated means exactly what it sounds like. We're all going to kind of sort of agree, but we're all going to be maybe a little bit different from each other as far as estimated digit. Now let me show you what I'm talking about here. Now everybody in here should agree that we are at least 7 centimeters. And by the way, these big tick marks is centimeters. The small tick marks are millimeters. Okay, so everybody in here should at least agree that it's 7 centimeters. All right, it's not 8. It's not 8. It's at least 7, right? Now, these tick marks inside here, and let me move over here. These tick marks in here, these tick marks, those are millimeter marks. Okay, those are millimeter marks. Okay, those are millimeter marks. And we can count across. We go 1, 2, 3, 4, and that's 5 right there. You see that? And then we got 6, 7, 8, 9, and then we got 10. Those are millimeter marks. And it's pretty typical in any sort of scale that halfway you have a line that's almost as long as the other lines. Okay? So I look at this and I see that I have at least 7 centimeters over here, and I count across. I go, well, that's 1 millimeter, that's point 0.1, so this is 7.1, 7.2, 7.3, 7.4, 7.5, 6, 7, 8. And if I'm looking here, and hopefully everybody else can see it, where I drew that line, it's not quite it's not quite 7.9. It's at least 7.8. Now, everybody in this room should be able to look at that scale and say, why, yes, sure, look, I see that. It says I can count. And hopefully everybody sees my little black dot, and we go, well, we start with the 5, and I go 5, 6, 7, 8. Okay, well, it's between the 8 and the 9, but it's at least 7.8 centimeters. Okay, that is certain. This is certain. The 7.8 is certain. Now, what we have to do is we have to estimate that last digit. Now, the last digit is in the hundredths place. That's 7.8 something. And so I look in here, and I am trying to estimate in between the lines. And I look in here, and it's at least halfway. Where I've drew my line, it's at least halfway. It's actually over halfway. And if I was to look at that, I would say that last line, now I'm going to go back over here, I would say it's 7.8 centimeters at least. And I'm going to say, just looking over here, just looking over here, I'm going to say that's probably like 7 points. That's probably 7. Okay, and that 7 is estimated. Okay, I estimated in between the lines. Okay, now you always estimate that last digit. Even if it's right on the line, that just means it's 0 if it's right on the line. So that number right there that I would, off of this ruler, this right here that I put there, I would say that it's 7.87. Now you may look at it and say it's 7.88, and you may look at it and say it's 7.86, but we should all say it's 7.8 something. It's 7.8 something. Now the primary skill here is you're able to count. Okay, and so you start with 7, and with 7 point whatever, and we go out 8 tick marks, that's 7.8, and we estimate between that 7.87. Okay, that's 7.87. Now, let's try on our own. Let me go ahead and erase this, and let's try on our own and see if we can do. Let's see what everybody gets. And when I ask you to do these things on your own, I'm serious. It's not like we're in a class where I can see you, whether you're doing it or not. But it's to your benefit to try. Oh, all right. And it's to your benefit to do that. So someone asked for annotation. So Chelsea Branton, what did you want to do?
That was actually an accident because I didn't know if we were gonna show you on the screen, and I didn't
Oh,
know we could
okay.
actually do that.
I
So
was so
that was kind of an
excited that you
accident.
were going to do something on it. I was so excited. Oh my God. Well, now I'm disappointed. Now I'm sad. All right, so
I'm
let me
sorry.
then I will change you out here. And let's see how do I do that? Let's just stop sharing, and then I'm going to go ahead and just start sharing again just so I can come back up here. And there we are. We're back to sharing. Okay. So what I'm going to do is I'm going to draw a line here. Okay, and I want to give everybody an opportunity here to tell me what it is that is the number that we're measuring. Okay, everybody with me? Okay, so what I'm going to do is I'm going to draw a line. Now I'm not much of an artist, but I'm going to try. Okay, right there, right where I'm pointing, right there. Okay, And I don't know why I lost my line that goes with it, but okay. But anyway, you see where it touches the ruler? Everybody see it? Okay, now write down real quick what you think that measurement is. Matter of fact, type it in the chat box. Everybody knows where the chat box is? Type in the chat box and let's just see what everybody gets, okay? 3.85 from Faith Mitchell, 3.87 from Justin, JD 3.87. Anybody
Mhm.
else? Yeah, it's popping up in my corner. We got Riley 3.85, Gungeon 3.87, 3.84, 3.86, 3. Hey, these numbers look really good to me. They look really good to me. And I'll tell you why they look really good to me, because first off, like Ms. Moore, what do we have here? I've got two decimal places. Okay? That means we're estimating that last digit. Now let me take a look, because you know what? I never know the answer to these things ahead of time. So I look here and I go 3, I go 5, 6, 7, 8. Yep, I would say it's at least 3.8. And I think everybody put up there when they typed in their answer, they had at least 3.8. And I'm going to look over here and I'm going to say 3.7. To me, it's greater than 5, that's for sure. 3.85. It looks like to me, to my eyes. Now, if you said 3.85, is that wrong? No, it's not. It's not wrong. If you say 3.86, it's not wrong. My estimate is 3.87. However, if you were to say 3.41, well, that's definitely wrong, because 3.4 is over there. You see what I'm saying? Now that's not right. That's not right. Okay. But, as long as you're 3.8 and then something else, well, it's just where you looked. Okay. Everybody clear on how to read that ruler? Okay. Now on the lab, we had you reading um, English ruler, and maybe we were reading like over here, and I'm not going to teach you how to read an English ruler. It's too complicated. You'll never have to do it again unless you're measuring for curtains. But in a lab, you'll never have to do that again. But what we do here is, in the lab, it's just estimate in between. That's 1 to 2 inches, so I know it's at least 1 inch. And the lab said to 1 decimal, it's over halfway. It's not quite 3/4, so I'm going to say that's probably about 1.6 inches. All right, and if you said 1.7, that's fine. If you said 1. Well, if you said 1.5, 1.5 is right there. So I would say it's either 1.6, 1.7, ish. Okay? And that's as far as we're going to go with measuring inches. Okay? Now, technically, what you do, I said I wouldn't show you how to do it, but, when you're measuring with a ruler, it's all about half, quarters, eighths, sixteenths, 32nds, 64ths. If anybody's ever worked in construction or anything like that, then you know what I'm talking about. And so you have to actually be able to add and subtract fractions. And so we never say 1.1 inches. We might say 1 1/4, or 1 1/8, or 1 5/16, or something like that. Okay. Another reason why we don't use English units is because they're painful to use compared to, say, metric. Okay. Now, when we're measuring, say, a graduated cylinder, okay, let me get out of that right there. I'm not going to save that. And let me pull up my whiteboard here. Let's say we're measuring with a graduated cylinder. Now, of the whole point of measuring is that you go one more decimal or place than certain. Now remember when I said we had at least 1.8, and I said, you know what, the estimated digit is 6, right? Well, what we did was we went one more decimal than we had certain digits. And so we're going to do the same thing with a graduated cylinder. Let's say we have a graduated cylinder and it's measured in milliliters. We have 1 milliliter, we have 10 milliliters, we have 20 milliliters, and in between I think your lab actually has a similar something similar to this. And in between, this is like right here, that line right there would be, let's see, 11, 12, 13. That would be 13 milliliters. That line. You see what I'm saying? Each tick mark's going 1 milliliter. And so if I was to measure using this graduated cylinder, now what's going to happen is that it's going to have a little bit of a curve to it. All right. And it's filled up to that point, and we're actually going to measure from the bottom of that curve. All right, right there on the bottom. That's where I'm measuring. And so if I do that, I know that, remember what I said about that medium-sized tick mark, that's halfway, right? And so that's 15 milliliters, 16 milliliters, and I would say this is at least 16 milliliters. All right, everybody in here, if you know how to read this scale, you start with 10. Each tick mark is 1. It's not tenths because we're going 10 tick marks from between 10 and 20. You would go 11, 12, 13, 14, 15, 16, 16 milliliters at least, right? There's 16, but it's above 16, right? But it's not 17. 17 would be the next blue tick mark up here. Okay, that would be 17. So it's somewhere between 16 and 17. So we have to estimate. And I look at this where I drew it in my very crude drawing. I would say that it's a little past halfway. And I would say, let me change the color here just to show that, estimated. So I estimated that last tenth of a milliliter. All right, now what did I do? I was certain, these were certain. In other words, everybody in this room should be able to say that it's at least 16 milliliters. And I had to go one more decimal over. Y'all see that? So don't get fixed on what my point is. It's not always two decimals. It's not always two decimals. It's always one more. It's always one more than what you have. If you got no decimals, in this case we had no decimals, you go over one more. So you would go from no decimals to one decimal. When we did the ruler, we went from one decimal that we knew for sure, and we estimated that last decimal, okay? So that's how you do measurements. So anytime you got measurements, you always, that last digit is always estimated. As a matter of fact, like this morning, I was standing on my scale. You know what a bathroom scale is? A bathroom scale is a device to torture you every day, to remind you that you shouldn't have eaten those hot wings the night before. All right, so this morning I've actually lost some weight since we've been on break. It probably has something to do if I'm not able to go out with my buddies drinking. Yeah, so they closed the brew pubs, so I've been losing weight. Imagine that. So this morning I was 188.6. That's what I weighed this morning. Technically my weight should be around 170. I'm about 18 pounds too heavy. And so, but if I step on this over and over again this morning, I cannot believe the weight. I'm going to step on it again. Now it keeps coming up 188.6. Okay. But believe it or not, internally, inside this device, electronically, there's actually a number in there. You can't see it, but it's there. So every time you step on it, that number is going to vary a little bit. Maybe not that much, but what you see here is actually a certain digit. It's the last digit that you see displayed, but actually internally, electronically, the last digit is hidden from you. And so if you were actually able to see that digit as you were standing on this scale, or as I'm standing on this scale, let's say that they didn't hide the digit on the scale. The 6 would stay constant, but I would see a 3, for a moment. Maybe I'd see a 2 for a moment. Maybe I'd see a 4 for a moment. Maybe I'd see a 3 again for a moment. Y'all see what I'm saying? There's electronic noise in there. And when we make a measurement over here like that, the fact that most of us get 6, some of us get 5, and some of us get 7 is actually noise. It's actually a form of noise. It's biological noise. But even electronically, there's some noise in here, and that's where it shows up in the estimated digit. You're going to be plus minus. You're going to follow some sort of distribution for that last digit. I'm sure if you've had stats, you recognize this. That last digit, most of us are going to say zero point 0.7, and then some of us are going to say zero point 0.6, and some of us might say zero point 0.8, depending, right? What's the area underneath this curve? Isn't it like 85% or something like that? You go out two standard deviations is what, 90, 95, and what, 3 is like 99 point something standard deviation, something like that. Okay. All right. So that's how you that's how you measure, and that's how you estimate. Any questions on this before I move on? Ask away. Y'all quiet. You see, if I was in class, I would look at you and I'd be like going, "Okay, Crystal, get off your cell phone." You know, or JD, come on, wake up. But I'm not. But you're not in class with me, so I can't tell. So if you don't say anything, I'm assuming that y'all are the most brilliant chemistry students that I've ever had, and y'all got no questions. Okay. All right. So let's do that then. So let's move on. But anyway, this is not the hard stuff. The hard stuff is coming later. This is the easy stuff. Okay, so let's go ahead and move on to what's called significant figures. Okay, significant figures is chapter 1, but it's also relevant to the lab that we're doing that's due Saturday. By the way, don't wait till Saturday to do your lab. All right, so we have significant figures. All right, so what significant figures does for you is like this. You can get a calculator answer, and your calculator answer may or may not make physical sense. May or may not make physical sense. Okay, and how does that work? Well, what it comes down to is there's something, I'm not going to write this down because but have y'all ever heard of like conservation of mass, conservation of energy, conservation of this and that, right? Well, there's a law of conservation for many things, okay? And they all basically say the same thing when we have conservation, whatever. They say you can't create whatever it is, you can't destroy whatever it is, you just kind of move it around. You can't create energy, you can't destroy energy, you just move it around. You can't create mass, you can't destroy mass, you just move it around. Well, the same thing's true for information. There's actually a law of conservation for information, believe it or not. Y'all may have never heard this, but it's true. And the idea is that you can't create information, you can't destroy information. All you can do is manipulate it and move it around. Okay, now this is important because check this out. Let's say that I make two measurements and I divide them. I have my ruler, my 50-cent ruler I got from Five and Below. Or maybe, I really splurged and went to Walmart and spent 75 cents on the ruler. Okay? But I can go out 2 decimals because we just did that with the ruler, right? We went out 2 decimals. And I put this in my calculator and this is what I get. My calculator gives me this answer, and by the way, internally on a calculator it keeps going. There's usually about 3 more places that you can't see in the calculator. Mine goes out 9 digits, but internally it's more like 12. All right, now you look at this and you say, well, what's the problem, Mr. Pierce? I mean, I don't understand. And I used to be in your position, believe it or not. There was a time when I was taking chemistry, and 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 calculators had just been invented. They really had. There was a time when there were no calculators in classrooms. because they hadn't been invented yet. And I was a freshman in college, and calculators had been around for just a few years. And we take these things for granted now. And I remember thinking, my gosh, because I was used to doing long division. I don't know if y'all know how to do long division anymore, but yeah, you get an answer, and I was like, my gosh, this is great. I don't have to do long division. I just plug in the numbers and I get these numbers. And my professor said, well, the numbers, you have to round them off. And I'm like, why? The calculator did all the work. I've got this beautiful 9-digit number. Well, the thing is it's not, doesn't make physical sense. I'm going to show you why. All right, so look, take a look at that 1.00 centimeters. What we're saying is I can measure out with that ruler. I can go out to 2 decimal places with that ruler. Right? Everybody agree? We just did it with the ruler. We went out 2 decimal places. With a 50-cent ruler, you can go out 2 decimal places. You can estimate that last decimal, that second decimal. You estimate that one, and we're certain for that first one. Right? We're certain. Okay. Now, when you tell me that this all means something, you're saying with a straight face, now look, I can say something reasonable out here. Even out here, I can say, I'm like, yeah, I've got, I can go out to a thousandths and the hundredths, and by the way, I get out here. When I get out here, what am I talking about? I'm talking about red blood cell. I get out here and I'm talking molecules. And if I get out here, I'm talking protons. And I get way out here and I'm talking fine structure of the universe. Fine structure of the universe, by the way, is called the Planck distance. It's as small can be. All right, fine structure of the universe. You mean for a 50-cent ruler, I can tell you something about molecules and protons in that measurement. Well, that's what you're telling me. When you're out over here, we're talking molecules and protons, right? You mean I mean all I have to do is take 2 measurements, put it in my calculator, and I can tell you something about the protons in that thing that we just measured. Do you see how ridiculous that is, right? But we get fixated. We look at the numbers and we say, "Oh yeah, the number. Hey, the numbers don't lie. The numbers are there." But they don't. They don't mean anything. So somewhere out in this area is meaningless. All right? And this comes back to the law of conservation of information, right? You can't destroy information, but you can't create information that isn't there. It isn't there. By taking this measurement of 1 centimeter by 3 centimeters, I can't tell you anything about the molecules and whether there's a red blood cell on it, or maybe even a COVID-19 viral particle. Okay, I can't tell you if there's one on there. It would be nice because I wouldn't have to spend, $10 billion on the what is it? CERN, CERN. It's a big super collider up in France and Switzerland, and it's a big 60-kilometer wide loop or whatever. I think it's like 60, maybe bigger than that, but it's huge. You mean we could avoid spending $10 billion and all I have to do is pull out a 50-cent ruler? That would be great, but that's not the way it works. So somewhere out in here it's meaningless. So we have to decide where to cut it off. And what we're going to say is that we have 3 digits of precision here. Precision, more on that in just a second. Let me erase this so it looks a little better. 3 digits of precision for both of these. And so what I'm going to say is the 3 digits of precision, in other words, how many digits can I measure? How many digits can I measure? Well, I'm going to say my answer shouldn't be any better than the worst measurement, the worst degree of precision that I have on my numbers. So I have 3 digits of precision for both of these. So I would say that it would be reasonable to say that this is 3 digits of precision. The leading zero is just to tell you that, there's a decimal there. All right, that's all it's there for. It's just to keep your eye on the decimal. So you got 3 digits there. So I would say the answer to this in a reasonable physical sort of way is 0.333. Because if we go out further than 0.33, we're adding digits of precision that we don't have to begin with. And if we cut it off too soon, let me do that in red. If we cut it off too soon, then we're throwing away information. And if we add on extra digits, we're adding extra information. You see what I'm saying? You don't want to add, you don't want to. Now, the book doesn't go in this, but I think it's important to not just throw out the rule, but to tell you that there is a sound physical basis for this rule. There's a sound physical base, and it comes down to information. So, how would we summarize this? So, here's the summary, and so we say the answer for multiplication slash division, yeah, I had that right, least significant figures. Now, what is a significant figure? Anything you measure. Anything measured. If you measure it, it's significant. All right. If you didn't measure it, in other words, you counted it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that's not significant. But if you measured it, it's significant. So this number, so this whole thing right here, I measured the whole thing, that's 3SF. And by the way, we don't ever say significant figures. We say either sig figs, and I will say sig figs all the time, or you say SF, one or the other. No one ever says significant figures. Well, occasionally you do, but generally you say sig figs or SF. Okay, so that's the rules for multiplication and division. All right, you go by the least number of significant figures and you go by the least number of measured numbers. Now, look, we're going to do significant figures for every single calculation that we ever do from now on. And if you take 152, you will do significant figures for every calculation that you do. So don't worry if it's a little awkward at first. Don't worry. It's like everything else that's good and fun in this world. It's always a little awkward at first, but we get good at it the more we do it. All right? And so, sure enough, with significant figures, it will be awkward to begin with and you'll get better at it. Now, let's take a look at the rules for addition and subtraction though. Now, addition and subtraction is a little different. Let's take a look at a series of numbers. And I'm going to add them together. All right, everybody see my green numbers? 124.281, 14.61, 2.1. All right. This is like 3 people took some measurements and they emailed them to each other and we're going to add them up. All right. And so I take this and I put this in my calculator and I will get a calculator answer. Now understand, significant figures is to take your calculator answer and turn it into a physically meaningful result. All right. It's not to take a measurement and round it. It's to take your calculator answer. That's what sig figs does, calculator answers. So let me get a calculator answer. So I don't need my calculator this morning, not for this at least. And hopefully I can do this without messing it up. And let's see, 8 and that's 10. That means carry to 1 and 1. Did I do that right? I think I did. 1, 9, let's see, 9, 4, 8, 10, 4, 1. Okay. This is my calculator answer. Your calculator answer may or may not make physical sense. And so I will ask y'all, and y'all can type in the answer. Type in the answer. What do you know about that number right there? What do you know? What is that number? Everybody tell me. What's that number? Just type it in. What do you think? Okay, Lauren says 0. That's anybody else? Come on, tell me what that number is. What do you think that number is? Let's see. What do you think that question mark is? What do you think? Crystal says 0. Riley says 0. Someone said estimated. Hannah says 0. Anybody else? What do you think? Wow, y'all are all in agreement. Wow, look at that. I can't get people. Ooh, Justin said 9. Yeah, there's always one in the bunch. Always one in the bunch. All right. And so, golly, yeah, I wish the world was like that. I wish I could get a whole room of people to agree on anything. But you're all wrong. Every single one of you wrong. All right. Isn't that the way life works? Is that the moment you start agreeing on everything, you find out you were wrong all along. Well, look. I look very carefully here, and I'm looking. Here I am this morning. There I am, bald headed guy. And I am looking with the eye of Ra. I don't know about you guys, but I don't see anything at all there. Do you see anything there? I don't see. I mean, I'm looking really hard. I really am. I'm looking really hard, and I'm not seeing anything there next to that one. I see a blank spot. That's what I see. I see a blank spot. And a blank spot means I don't know nothing. I don't know anything. I don't know anything about that number right there. I also don't know anything about that number, and I don't know anything about that number. If you didn't measure it, if you didn't measure it, you don't know anything about it. How can you possibly? I mean, you didn't know. You don't know. This guy up here, he didn't go to Five and Below. This guy, he went to, let's say, Harbor Freight. He got his ruler from Harbor Freight. This guy went to Walmart, got his ruler. He could measure out the 2 decimal places. And this guy, well, he just pulled out his tape measure. The more money you spend on something, the more digits of precision you get. But look, there you can't sit now. If I go back and remeasure this number, if I remeasure, it could be 1, it could be 5, it could be 7, it could be 8, could be 0, could be any one of these numbers, could be anything if you go back. But since I don't have anything there, I don't know anything about it. You just don't know. If it's not there, you don't know. So what I do know for sure is that number is at least 1. How do I know it's at least 1? Because you added 1, right? It could be 1 plus 0 plus 0, which would be 1. It could be 1 plus 9 plus 8. It could be 1.5, 1 plus 5 plus 2. It could be anything, but it's at least 1. And I do know this is at least 9. Okay? But here, right here, I know it's at least 9. Okay? I know. Because I know there's a 2 there, I know there's a 6 there, and I know there's a 1 there. I know. I only know what I know. I mean, that sounds like, an obvious statement, but you only know what you know. If you don't know it, then you don't know it. And so I know it's 9. So I know I can safely say that the answer is at least 140.9. I can remember that. You see that the language I'm using here, like when we did the ruler and the graduated cylinder, I said we know it's at least blank, right? And then we had to estimate. This last digit here, though, that 9 right there, well, I know it's at least 9 because 8 plus 1 gives me 9, but that's all I know. I know it's at least 9. So you can kind of say that's an estimated digit. So what do we do with estimated digits? We go one more over, and then we round. So if it's 5 or greater, we round up, and if it's 4 or less, we round down. So the answer is 141.0 because I rounded up this 9 to 10, and that made it that 9 turn into a 10 as well. Okay, so I rounded up. Because I knew it's at least 140.99, the only digit that I know for sure is that 0.9. That's the only one I know for sure. So it comes down to information. You don't know what these guys are right there. You just don't know. And if you don't know what they are, you don't know for sure what these are. So y'all see that? Y'all see how that works? Do you see how it comes down to information? It really does. So what is the rule for addition and subtraction? Based on this, you would say for addition, subtraction, you go by least decimal places. All right, not least significant figures, least decimals. So we had 3 decimals here. We had 2 decimals here after I marked all over it. Maybe y'all can still see that. And I had 1 decimal here. So my answer needs to be 1 decimal. And so sure enough, that's 1 decimal. Y'all see that? Go by the least number of decimals. Addition and subtraction, least number of decimals. All right, questions on this so far? All comes down to information. Conservation of information, as a matter of fact. All right. Now let me show you something. Now, oh, by the way, while I'm thinking about it, in reality, because we deal with reality, the only time you worry about addition and subtraction with sig figs is like test, quiz, and homeworks. In the real world, if we're like taking the difference between two temperatures, let's say we want to know that the temperature went from, say, 15 degrees Celsius to 25 degrees Celsius, what would we say the answer is? Well, the calculator answer is 10, but we already know that we go by least number of decimals, so that's actually 10.0 degrees Celsius. Okay? When we do measurements in temperature, we will often do to 1 decimal. All the measurements will be in 1 decimal because we're using the same instrument to do all the measurements. So it kind of naturally follows that if you take the difference between two temperatures and you go out to 1 decimal, you ought to have your answer to 1 decimal. Just because that's what you measure temperature to is 1 decimal. If you're measuring out to 2, both of them will be 2. It's only when we have these funny little situations like this right here. This is like 3 different people using 3 different kinds of rulers. It's not going to happen. But you still have to be able to handle it, is the point. Okay, you still have to be able to handle it. That is the point. Okay, so one more thing, and let's take a look here. Now here's something that comes up. Let's say we had 12.48 times 25.0 minus 3.15. Well, let's make this. Let's do it like that. Okay. All right, and I want to know what's the answer to the correct number of sig figs. So we have two things going on here. We have multiplication and we have addition going on. Right? Now y'all know order of operation, right? You do powers first, multiplication and division second, then you do addition and subtraction last, and if it's inside parentheses, you do them first. So what we should do is we should do it according to the rules of sig figs. And so according to the rules of sig figs, what's the rules of sig figs for here? Least number of decimal places. And so our answer would be, our calculator answer is what? 25 minus 3.1. Let me turn on my calculator first. 25 minus 3.1. And I get... Huh? Go ahead. Or was that background noise? Okay. Alright, so we got 21.9 is my calculator answer. But according to the rules of sig figs, I have 0 decimals here, 1 decimal here, so our answer should be 21. It's actually 22, sorry. Got to round it. 0 decimals, 0 is a number. 0 through 9, not 1 through 9. Alright? And now we say 12.48 times 22. And We do that. And so I say 12.48 times 22 gives me a calculator answer, 274.56. We have 4SF, 2SF, and we go 1, 2, look one more over, and that is 270. That's my answer, and this is two significant figures. Now, an alternative way of doing this is you don't do anything to the end, and we put everything, and this is the way I prefer to do it, is 12.48 times parentheses 25 minus 3.1 close parentheses, and I get a slightly different answer. Let me change colors here, and I get 273.312 as my calculator answer, but I look here and I say, well, this is going to end up being 2SF here. This is going to end up being 3SF here. And so our answer should be 2SF. So we go 1, 2, look one more over, and it's still 270, which is 2 sig figs, 2SF. You see that? All right, so you have to apply different rules depending on what you're doing. Depending on what you're doing, you have to apply different rules. All right, like I said, the more you do this, the better you'll get at it. We will do significant figures for every calculation. 99% of the time, it'll be multiplication slash division.
I have a question.
Yeah, sure, go ahead.
If the answer was above 275, 76, we rounded to 280 to make it
275,
2.
76 to 2SF would be 280.
Okay.
2SF. How do we do that? We go 1, 2, we look one more over, and we round it up. Now we have to add that 0 in to keep the same size, because 28 is not 280, right?
Yeah.
28 is not the same size as 280, so don't do that. Usually it's not a problem in 151. But yeah, exactly right. If you got 275.76, you would look over, you'd go 1, 2, look one more over, round up to 2, 28, add that 0 on so that you have the right size. So when we're looking at, does that answer your question?
Yeah, thank you.
Okay, now when we're looking at numbers and we're trying to round up, there's only two things you have to really worry about. First off, leading zeros are never significant. Never significant. And then trailing is not significant. Trailing zeros, should I say. Not significant unless a decimal somewhere. So if I have, how many sig figs is that? Well, these are leading, so they don't count for anything. So this would be 3SF. How about this one? How many sig figs there? Well, these are trailing, no decimal, so therefore it must be what? 4SF. How about how about what do we got there? Well,
4.
that's trailing, right? But it has a decimal. It has a decimal, right? Unless, well, let me make that look just a little better. Unless a decimal somewhere. So there is a decimal. Look, there's a decimal right there. So that makes everything significant. So this is 5. Okay? Trailing zeros are not significant unless you have a decimal. 157200, there's no decimal, so the zeros don't count. 149.20, well, that zero is now a measured zero. You just happen to land on zero. It's like I step on the scale tomorrow, maybe to 188.0. Does that matter? Well, yeah. Could have landed on point 0.1. It could have landed on point 0.6 like today. But it happened to land on zero. But there's a decimal there, so that makes it measured. It makes it significant. All right. Matter of fact, if I take this same number over here and add a decimal, guess what? It's now 7. See the difference? See, what we're really saying is we can't measure any better than those 4 digits over here. Here we're saying we could measure out quite a ways in digits. And in case you're wondering, why wouldn't we measure all the digits all the time? I know that at least one of you is thinking this, because I thought this when I was in your position. I was like, well, why can't we just measure all the digits all the time, right? It comes down to cost. It really does. If you want to measure out with a ruler, if you want to measure out to 2 decimal places, you're talking 50 cents. You want to measure out to 3 decimal places, and actually there's no 3's, usually you go straight out to 4. 4 decimal places, you're talking 80 bucks. If you want to measure out even further, like maybe 8, you're talking, 10 grand. All right, the more digits you can measure, the harder you have to work for it, the more it costs. So the reason why, that this, you're not measuring over here all the way out, to 7 significant figures for there, it probably just comes down to cost and how much effort, and is it worth it? Is it worth it to do it? If you go into the lab and you measure stuff, you have a choice between different scales. You sure do. And one scale will measure out to 5 places, and the other scale measures out to 3 places. Well, that one that measures out to 3 places costs us 200 bucks. The one that measures out to 5 places costs us 1,200 bucks. You see what I'm saying? The more digits you have, the more it costs. That's why you have things have different numbers of measured number of digits. Like for instance, when I step on my scale in the morning and it said 188.6 pounds, right? That 0.6 is good enough. If I wanted to buy a scale to measure me out to 1.65, if I sneezed, I would lose part of that. By the way, that point whatever pounds, what's a tenth of a pound? That's 1.6 ounces. So you can go drink a cup of coffee, come back, and you're going to weigh, 0.66 or 0.68 if you drink a cup of coffee. That's not very useful at all. But you'd have to pay more. Instead of being 30 bucks, this might cost 400 bucks. So it comes down to cost. Everybody see that? All right, so what we're going to do is we're going to take about a 5-minute break, okay? We're going to start back up at 11. Everybody got that? Don't disappear on me, because we're going to do dimensional analysis next, okay? So let's take about a 5-minute break, stretch your legs, whatever. All right, so I'm going to go stop recording. Let's see, and supposedly I can stop this. So I'm going to stop this from recording. I'm going to stop sharing, and it should allow me to do that. Stop. There it goes. All right, I'm not recording anymore. So 11 o'clock, all right?